Hi, my name is Thomas Weible from Flexoptix, co-founder of Flexoptix, and these days mainly in the technology environment when it comes to pluggable transceivers. And this presentation here today, which is the second slide, is more an outlook what will happen this year and also next year when it comes to transmission speed of 400 gigabit. And it's split in two sections. So I got, first of all, to understand the 400 gigabit technology a little bit in detail. I have a theory part, which I will introduce at the beginning, and then later on we do some hands-on. I did this presentation also on the RIPE meeting last year, and afterwards Aaron from Six Connect came to me and said, hey Thomas, you have to rename your presentation because it's something like from Cyclops to Triclops. So what you present there is yeah, you have something with 3 eyes and some interesting monsters. So let's start. From the theory, and that's really a straight theory back to high school time, when we talk about 400 gigabit, this is a typical signal of representing one big bit. So we have a rectangle shape, like that. So we got a rectangle shape of our digital signal, and it's representing one bit. On-off keying, pretty straightforward, and having 2 events here. So we got a H, the high event and the low event. And when we have a defined frequency, like 10 gigabaud, for example, we can transmit 10 gigabit because we got 1 bit per symbol. Now, when I talk to network engineers, and also there's sometimes a term coming in called an eye diagram. A lot of people say, yeah, an eye diagram, I know what it is. But when you ask, hey, do you understand, or what is the meaning of an eye diagram, then basically the conversation stops. So the main goal is, when we talk about eye diagram, we want to have a beautiful and open eye. That's a really important thing, but why is it so important? Let's start with a sequence of 3 bits, basically. So I represent here a sequence of 3 bits, starting 0, 1, 0, going throughout event low, high, and low. Now, having a sequence of 3 bits and 2 events, so this is 2 to the power of 3. In total, this would give us 8 different states. So these, here you can see those different states. As I said, beginning is 0, 1, 0, and we got 1, 1, 1 or 1, 0, 0. Choose any of them. So what we do now is, when we overlap them, all 8 of them, we get something which looks a little bit like this down there. So we overlapped all 8 different scenarios, and this basically looks a little bit like an eye, which we see up there. So what makes an eye diagram? It's mainly, this is what we see here is the high-speed curve of a 100 gigabit transceiver measured with a scope. Starting from here, from the high event, going down to the low and up to the high again, and all different states. So that these are the overlap ones, and it's the same up here. But the interesting part is that shape in the middle. So that really makes the eye diagram an eye diagram, because what we want to avoid is that our transmitter is going through that shape. Because when it would go through, on the other side of a transmitter, we do have a receiver, and this receiver needs somehow to determine and to detect, was it a 0 or was it a 1? And if he can't detect if it was a 0 or a 1, a clear open eye basically, then it's garbage. There's nothing between 0 and 1. So then we get bit errors. So the main target is really having a clear open eye, and the more and open it is, the better it is, basically. So what you really want to avoid, and that can happen with dodgy transmitters, or even if you have a long distance transmissions on broken fibers, you want to avoid a dodgy eye, a broken one. This was me trying to play ice hockey. I wasn't very successful. So let's move on. Now, the presentation started with 400 gigabit, but so far we hadn't talked about 400 gigabit yet. Yes, what I showed in the last slides was more about state-of-the-art technology up to 100 gigabit. But now, when we want to move towards 400 gigabit, we have to tweak our signal a little bit. For sure, we could just increase the frequency 4 times, then we would have 400 gigabit. But this is very expensive to do so there are some other ways to do it. And that's what I want to show now. So we still have our signal here again representing in this situation now 2 bits. So same frequency, but we double the amount of data now encoded with that signal because we added 2 intermediate events in there. So we got our low event, and now instead of only H, we got H1, 2, and 3 now. And how is that done? So that's basically a modulation scheme, how we do it. The eye diagram would look like this. This is the monster with 3 eyes. This modulation is called pulse amplitude modulation 4 level. So we got the 4 levels, low, high 1, high 2, and high 3. And this represents here 3 eyes then in there. And the great thing is now, instead of having a symbol now with 1 bit, we have a symbol rate of 2 bits on the same frequency. So we got the symbol 0, 0, 0, 1, 1, 0, and 1, 1. And that's pretty great. So we just, due to the effect of the modulation, how we modulate it, we double the amount of data we can transmit on the same frequency. And that's one key component when we talk about 400 gigabit modules or pluggable transceivers, that they are all based on PAM4 modulation now. But PAM4 only gives us the possibility to double the amount of data. So from 100 gigabit, we would end up at 200 gigabit. And how we will end up at 400 gigabit, I will show now on the hands-on section. So first of all, we need to do a recap when we open up 100 gigabit transceivers in these days. So the latest generations of 100 gigabit transceivers, they have electrical side on the left side, which you see here. There is the connector facing towards our host, and this is driving 4 times 25 gigabit, 4 lanes basically, 4 times TX, 4 times RX. And on the optical side in such a transceiver, we got 4 optical engines, 4 lasers, 4 receivers. That's straightforward for 100 gigabit pluggables. Now for the 400 gigabit, first of all, we do have the PAM4 modulation in there, so we have 2 bits per symbol. And on the electrical side, what we can see here is we have, instead of 4 lanes, we have 8 lanes in the future. So a pluggable is driving 8 lanes TX, 8 lanes RX, and running at a speed of 50 gigabit, and that's PAM4. On the optical side, pretty much the same setup. We got 8 optical engines, TX side and RX side in total. So this will be the first generation for 400 gigabit transceivers. When there is a first generation, there will be a second one. The second one will look a little bit different, so the electrical side won't change. Beside the fact that there will be placed a gearbox in there. A gearbox is, at the end of the day, is a chip, and it does a conversion from 8 lanes, combines it to 4 lanes, running an optical engine with 4 times 100 gigabit, still PAM4 modulation there. And now there might be the question, hey, why is the need to put there a gearbox and not instead doing it like on the 100 gigabit world, running 4 times 100 gigabit straight out from our host? The issue is basically costs. A chip is way cheaper than increasing the frequency on our PCB, because when you increase the frequency that much, then you need different PCB material, and that's really expensive, like ceramic or to produce so. And it's always the target when you build these modules in high quantities. You want to cut down the costs. That's one thing. So a chip is cheaper. And how do the packaging look like? You might be familiar with the last generation of 100 gigabit is the QSFP-28 form factor as a pluggable. And there will be new form factors introduced for 400 gigabit. It's either the QSFP-DD, and it's pretty much the same size compared to a QSFP-28, and another one called the OSFP, which is slightly bigger. So the proportions are pretty much the same, but it's slightly bigger. What is so interesting about QSFP-DD here in the middle? The QSFP-DD is backwards compatible to a QSFP-28. So when you have a switch with the QSFP-DD slot, you can plug in a QSFP-28 pluggable. That's pretty cool, because then you have your 400 gigabit switch. You can either run 400 gigabit transceivers in there or even 100 gigabit transceivers. How is this made? We got here an electrical connector, and the QSFP-28 has a golden finger connector with one row, and the QSFP-DD basically has two rows. So when you plug in a QSFP-DD in a 400 gigabit switch, both rows will connect. But if you instead plug in a QSFP-28 into a QSFP-DD slot, only the first row will connect, and then the second one is not used. And that's pretty handy. What else is to mention about those form factors when we talk about the sizing? I mentioned the portion which sticks out of your first unit of your switch, for example, and the bad news is it won't change. So we have seen that maybe for the first 10 gigabit DWDM SFP pluses, when they were introduced, they had a big heat thing at the front, and we got calls from customers saying, hey, we have an issue now, we can't close the rack door any longer because they stick out that much that the cables will bend too much. So hey, can't we get them smaller? And the bad news is it's defined now by MSA that the transceivers are allowed to get out about 35 millimeters, and keep that in mind, that this is an important thing, because you need a little bit bend radius also for your fiber, and also the LC or the plugs, they need also a little bit space. So you might end up having around 150 millimeters space in front of your first rack unit. And when you're looking at the latest switches, which are have a big depth, then the second rack unit will be somewhere at 750 millimeters, and then you might end up that a 1000 millimeter rack won't be sufficient any longer, because you also need a little bit space for power plugs, etc. at the back end. For sure, the heat somehow needs to dissipate as well. So you might end up using racks with 1200 millimeters in the future when you look at the whole ecosystem of such a switch. So, and now the main question is what we can connect here on those 400 gigabit transceivers. For sure, we can back-to-back connect them, 400 gigabit QSFP-DD to OSFP, for example. That's, I think, pretty straightforward. But there will be some new applications coming out as well, and you might also already use them in 100 gigabit already with the breakout mode, like in 4 times 25 gigabit, or when you look at 40 gigabit at 4 times 10 gigabit. And that same thing can be doable with 400 gigabit. So we have either QSFP-DD or OSFP, and we can break it out to 4 times 100 gigabit. But this 100 gigabit, what we break out here is a single lambda PAM4 base, and that's really important. So we got 4 lambdas or 4 wavelengths driving each 100 gigabit. And this, you can either connect them to a new generation, second generation basically of QSFP-28, which can also do PAM4, a single lambda, single wavelength, 100 gigabit, or even newer form factors for 100 gigabit like the µQSFP or the SFP-DD, which will be launched in the next couple of, or by 2019 or 2020. And I think that's pretty handy. And it's also good to know that the 400 gigabit is quite a flexible technology, because it's not only 1 time 400 gigabit. You can also do 2 times 200 gigabit with that standard, and also 4 times 100 gigabit. So you have a quite big choice of applications there. And when we talk about standards, we also have to take the IEEE in consideration. And I represent here now, and that's a recap again about 100 gigabit. When we come to IEEE and 100 gigabit, there was not a lot of definition when we talked about single mode, what we can do with the IEEE on single mode. That was mainly LR4. And LR4 defined, okay, up to 10 kilometers, and we have a spacing between the 4 wavelength of 5 nanometers called the LAN WDM. Now, for sure, in practice, there were some other applications out there like the PSM, so that's this breakout mode which I mentioned, the 4 times 25 gig, but there was never an IEEE standard. And the same applied to CWDM4, or also called as CLR4. This term is in the industry well known, but it was never defined by IEEE. And that's one reason, for example, when you go to your exchange point, you don't see those interfaces there because it's not standardized. So when there is a standard, then you can talk against this standard. That's quite helpful, and therefore only the LR4 was there. These lessons were learned also from the IEEE. And for 400 gigabit, they introduced two new definitions. First of all, the DR4, that's this old parallel single mode transmission, 4 times 100 gigabit now, up to 500 meters. And also they introduced the FR4, which is the old well-known CWDM 20 nanometer spacing between the waves, up to 2 kilometers. And both of them are mainly interesting for data center interconnect, so within data centers basically, up to a reach of 2 kilometers, and this is quite sufficient for the most data centers in these days. For sure, there will be LR4 and as well, up to 10 kilometers again. But why was it introduced? Industry saw in the field, in the terms of costs and money, that the CWDM technology, which is here shown, the FR4, is way cheaper to produce than the LAN WDM LR4, and it's just driven by cost at the end of the day to introduce that one. Right. This FR8 and FR4, or LR8 and LR4, it's basically what I show here is the first generation, because we don't have a gearbox in the transceiver, so it's 8 lanes, and the second generation will be 4 lanes, and the same applies for LR4 and LR8. When we come to another point is power consumption. That's one key component for 400 gigabit. Again, lesson learned from 100 gigabit. When we look at the last generation, these pluggables were allowed to consume up to 4 or 5 watts of power, which is not a lot. And when we see what kind of applications we can build there, the longest transceivers we got out there is up to 25, 30 kilometers doing 100 gigabit. And that's mainly due to the effect of the power consumption. Now, for 400 gigabit transceivers, the power consumption got raised much. So a QSFP-DD as form factor will go, by definition, can go up to 12 watts, and an OSFP up to 15 watts. First of all, the question why the OSFP can do more, it's just pure physics. The OSFP is bigger, and it has an integrated heatsink in there, and that's a key component when we want to get. First of all, we want to pump in that energy. That's one thing. And then we want to get out of that heat, because that's what we generate basically all in our data centers. We generate a lot of heat. And so 15 watts on such a small module is quite a lot of heat, which we have to get rid. And when you do the math, for example, when you look at latest switches now, which has been launched last year, one was from Arista, the 7060 platform, they will have 32 ports carrying OSFP. And when you do your math, you will end up with roughly 500 watts just in power or heat dissipation only for the optical transceivers. Not taking into consideration that there is power supplies, that there is RAM, CPU. This also needs a little bit of power, so we might end up with 1U switches having up to 1 kilowatt of power consumption and also heat dissipation there. For QSFP-DD, it's a little bit of a bigger challenge to get there, because it's basically built a little bit smaller, and but yeah, that's basically for QSFP-DD. But the main question now is, why is it so important to pump in that much power in such a transceiver? And the answer is, again, lesson learned from 100 gigabit. We want to get beyond those 10 kilometers or even the 25 kilometer landmark. We want to get there again where we are at 10 gigabit pluggables. We want to do DWDM 80 kilometers. And that's only doable when we do something like coherent DWDM. And to produce a pluggable transceiver which is capable to do coherent DWDM, we need a signal processor in there. We need a lot of power just to feed those chips. And for sure, we have to get rid of this power as well. And those 15 or even 12 watts are sufficient to build a coherent DWDM 400 gigabit pluggable. And I think that's the major improvement when we look on the roadmap for the next couple of years, that yes, there will be again pluggables doing DWDM, and we are not stuck where we are at the moment with 100 gigabit, where we need transponder systems with built-in coherent 100 gigabit DWDM transponders. So I think that's the major improvement there, that these 400 gigabit transceivers will be able to have that. When you ask me when are they available, the answer is I don't know. For sure, first of all, the typical legacy gear like 10 kilometer LR4 or even DR4, FR4 will be the first one which will be published by the beginning of this year. And then with the ongoing development, we will see the coherent DWDM ZRs. But I doubt that we see them in 2019. I'm pretty sure it will be 2020 or even later to build them there and to have them available. Yeah, the race is open. The first switches are out there. We will see which form factor will make it, either OSFP or QSFP-DD. It's interesting to see that, for example, Arista is one of the first publisher of 400 gigabit switches. And interesting is they are driving the OSFP quite much. They are one of the main driver there for the OSFP. All the rest of the industry is focusing towards the QSFP-DD as a more flexible pluggable. But Arista also produced their 7060 platform also with QSFP-DD pluggables. And it's interesting to see what's going to be available also from the other vendors in the future, and also which form factors will make it. Yeah, that's roughly the overview about 400 gigabit. For us itself, as Flexoptix, there will be a lot of freedom also with the microcontroller inside of the transceiver to tweak them. We did this lessons also with 100 gigabit transceivers to get them up and running in legacy gear. And I think this will also be a task and challenge with the 400 gigabit ones. Thank you very much for listening. If you have questions, I'm happy to take it.
Hello, Joe from TrueSpeed. What are the limits on power in and optics out? I mean, ideally you want to put electrons in and turn it all into photons and not have any heat at all, but there must be some physical limits that get worse as we scale up. Is there a limit to what we're going to be doing with this, and is it an efficiency issue? Is it a gearbox issue? What does that look like? You mean in terms of speed, or in terms of heat dissipation, to reduce the heat dissipation and get more efficient communication? It's in general, it's mainly you have to the components which you are built in, like a DSP or the PAM4 chip. The goal is to build them in a power efficient way. You might can do a little bit of comparison with what we have seen in the past. When you look at 10G base T, at the beginning when 10 gigabit was introduced, there was no 10G base T pluggable available, although there were switches where fixed 10G base T ports were in there. And the reason was the chips were available, but they consumed too much power. Like on that footprint on SFP Plus, you're only allowed to take 1.5 max 2 watts, and those chips which were available in these days, they took up to 7 watts. So you were not able to build it in. And then suddenly someone came around and said, okay, we can build a chip with consuming only 1.5 watt, and also in mass production like 100 million pieces. It's always, in theory, a lot of things are possible, and 400 gigabit is already there. When you look on transponder cards as a fixed optic, but they are big. And the bigger it is, the easier it's built. But our target is we want to have it in a pluggable module, small footprint, small form factor. That's the goal. And the smaller it gets, the more challenge it is to have the right components with the right power consumption and dissipation. Okay, so when we're building transmission networks to scale into the future, we're putting in, say, if we're putting a cabinet, we build cabinets in villages. Say, if we put a cabinet in a village and it's got top-of-rack data switches in it, and we've got a certain amount of heat capacity we can take out, we expect over time to replace the equipment with other equipment. And what you seem to be saying is you've also got to, if you want to carry on doing that ad infinitum, unless there's an efficiency that can be recovered, you've also got to have a capacity that's more than you're budgeting for now in order to go faster speeds. How do I understand the limits between what might be possible versus what's available on the first generation of tech? Sorry, I can't answer that question. I don't know. I'll talk to you offline. Okay, thank you.
Okay, thank you, Thomas.
Okay, thanks.